Yeah, because last time Xin has given a very short introduction about quantization methods for large language models. I feel this is a very, very important topic, and we need to yeah, because last time Xin has given a very short introduction. Yeah, we need to learn more about details. That's why I asked Xin to give a more detailed introduction about works in this line of research. I'm not sure if today is enough for her to introduce everything, but I think Shane, you should introduce the most popular or state of art in quantization methods for LLM today, and then we can find some time to, for example, next week to introduce more.
Okay, sure. Yeah, so today I'm going to talk about the basic quantization method, and also one most popular quantization method this year. That's the QLoRa. So I think I will just introduce them today, and maybe we can cover the other state of art next week if we plan to do that. So yeah, so as for the so firstly, I still want to have a basic introduction of the large language model. So as we know, this year GPT-4 is very popular. It has so many different applications. So somehow like write Python code and even compose music and or do some mathematical problem, or yeah. So due to its large application, so there is very hard there are very hard research on the large topic, large language model, and we can see that the large language model size grew very quickly every year. So from the basic model is transformer. Initially, it's only a few million parameters, and when it comes to the GPT, and even for the GPT-2, GPT-4, it comes to 1.5 billion parameter for GPT-2, and yeah, and in this year for GPT-4, actually there are even much larger model size. So the problem is that the problem is that the current GPU memory is relatively small compared to the model size. As we can see that the most powerful GPU for now is A100. It only have 80 gigabyte memory. So for the training and the inference of the large language model, it requires a lot of GPU resource. The problem is that possible for us to use some limited resource to train or do the inference on the for the large language model. So that's the motivation. And the one very hot topic of this year is that, yeah.
If the current model needs so many parameters, even 1 trillion parameters, how do they train their model? They have the GPU cluster?
Yes. Yeah, so so I think there is the distribution of the training technical. So in the large company, so they may have thousands of GPU and train for somehow like the 30 days to get a very trained large language model. yeah, it's very resource compute
Yeah, and
instant.
I'm curious about how you use Chat GTP or large language models to compose music. So I guess they convert the notes of the music into sequence of tokens.
Yeah, I didn't know the detail of that, but I think it's somehow it's called the multimodal. So for the multimodal, it means that it tries to have the different type of input. It can be image, video, audio, or large language model. So it somehow need to match the representation of different type of data. I what I know for the mapping of the representation between the image and the text can use the clip. So that's a contrastive loss to learn the mapping between the representation of the image and the text. And for the other type of data, so I guess maybe there are similar methods for that.
Oh, really? I thought you're gonna have to concatenate or pipeline it with some generative model to produce images. So when you use large language models, you can directly produce sequence of images. Yeah, I'm just curious because like 15 years ago when I was a student in Chinese Academy of Sciences, my boss at that time wanted to create an automatic animation generating system. So there was one academic fellow in China who is known for that. Like he wants to build up system like when you give a test script of the animation, then at the end of the system they can generate the cartoon animation directly. But they are totally based on logic reasoning system. It's called first order logic. You guys might have never heard of that. That was once were a key topic in artificial intelligence. I was an expert in first order logic before.
Okay.
Yeah, but I guess they will never be able to produce a well-performed system. But nowadays, like if you have a large language models, you got generative models, right? Generative models can convert a text into some images, right? So if you can stream a sequence of text snippets to describe the story, and then pipeline to the generative model, I guess they can produce the cartoon as well.
Yeah, yes, I think the now for the GPT model, it can do a lot of things. So,
yeah, I'm not sure like if the current state of art they have already they do not need to directly call some generative model. They can directly generate sequence of images. That is the video, right?
Yeah, so I think it can do that, but I'm not very but I don't know the detail about the technical there.
Yeah, go on. Please go on.
So sorry, Xin. I have a little question. So what does the figure means? Is that means the model will hit to the memory wall before they hit the computation wall?
What do you mean the memory bound? So you mean
And
the
I mean, what does this picture mean?
yeah, so actually there are two curves, right? So for the purple one, that's the increase of the model size. So for the model, I think it's some it's just indicate how many parameter one large language model have. So it can, for the largest one, currently it have about 500 billion parameter. And for the yellow curve, actually that's the GPU memory size. So it's somehow how much the gigabyte. So for this figure, it shows the gap between the parameter size and the current GPU memory.
So it seems like the memory is not able to support the current big model parameters.
Yeah, sure. So actually there are some different technical for that. So one very popular thing is that one large language model will be divided into separate part. So it will just fit one part into one GPU. So with so somehow like that, we have 10 parts, and then we put 10 parts into the 10 GPU, and the whole language whole model training still can hold sequentially in those 10 GPU. So that's one technical to solve this problem.
Okay, thank you.
All right.
So I have a question. So GPT-4 can generate images?
Um,
This was the question I asked Xin. I just asked.
Yes.
Not sure.
Yeah.
Yeah.
So I'm not very understand why it can generate image.
Okay. So yeah.
So it first generate text tokens that it feed to you said if it feed to Clip model.
Actually, maybe I can show some
feature alignment auto models.
Yeah.
Okay.
So
yeah,
as what?
Okay, go ahead.
Okay. I mean, when I use the ChatGPT itself, because GPT-4 is what behind the ChatGPT, right? So when we use that, I think it only provides the text generation, and so what I know that when people want to have to use the multimodal, actually it always have some adapter. I mean, it will have the other modular to support the image generation. So it's not just the large language model itself. I think I know some open source multimodal project.
Yeah, I'm not sure. So based on my understanding of multimodality models is that the inputs are multimodality. I don't understand why you can put no, you can, yeah. Yeah, you should train an offline adapter that align those features.
yeah, I think it's best for me to find some figure to show that it's
Okay,
not
yeah.
adapter. So in
Okay.
general,
Okay.
adapter is always used to do the fine tune. So somehow fine tune on small data set. But I think if we want to do some multimodal task, it also maybe require some VIT modular pre-trained on the large image data set, and then combine the VIT and the large language model together, and then there is still a third modular to combine their representation and do the generalization of the image. That's what I understand the process. So yeah, so I think the VIT model and the large language model are pre-trained, but the third modular to combine them and do the generalization of the image need to train.
Yeah, go on. Sure.
Okay. Yeah, I'm trying to.
And then never mind. Just curious.
Okay.
You should dig out some like fancy applications. Right now, people are trying, because you know you're looking for jobs, right? You need to associate what you're doing to what kind of promising applications that will be. That's very important.
Okay. Yeah. Thank you. So yeah, I think I've found some good figure to show the application.
Yeah, but for now, let's save time. Just go to the next slide.
Okay. So yeah, I think the motivation for motivation here is that when for both the training inference and the deployment. So how can we do them in a resource limited environment? So somehow like that, is that possible to do the training, to do the inference, or even the training of the large model on a single GPU, somehow like on the A100 with the 40 GB memory. So there is one very hot topic, that's the quantization. The basic idea for that is that possible to represent the model with less bits. So for now, the large model always have 16 bits for every weight instead of 32 bits, because yeah. So for that, it can save the memory, and today, firstly, I would like to introduce some motivation how to do the quantization. I will use a very simple example to show the basic quantization techniques. So in this slide, we can say that we assume we have a bunch of data, and the range is from -10 to 10. And we can say that for those data, actually they are not evenly distributed. The first very basic quantization method is round to nearest. So it somehow like that. Assume we only have 2 bits for the whole data. It means that we need to use the value from 1, 2, 3 to represent all the data range from -10 to 10. So we can divide the range from -10 to 10 into four area evenly, and then for every data point in one part, in one range, in one area, we can use the middle value of that area to represent that value. So somehow like that. So for all the data allocated in this range, we can just use a 0 to represent this. And so we will have some mapping between the index and the real value. And in general, it will firstly scale the original range -10 to 10 to somehow like the -1 and 1. So we will have a different value for them. I think this is minus 0.5, 0.5. Yeah, so for all the value in this range, it will be mapped to -0.75, somehow like this. And so after quantization, we only have for such data. So this was -0.25, 0.75. Yeah. So as we can see that this will lead to large quantization error. So this is a basic method called round to nearest. Is there any question for this?
Yeah, I have a stupid question. So I understand the basic idea. They want to so how the quantization save the memory ideally, but I have a so why how they store the 0.75, 0.25 the median numbers in memory. So based on my understanding, this is still a flow, right?
Yeah. So actually, once
they have some mechanism.
Yeah, actually there are a few there are steps for the quantization and the dequantization. For the quantization, it will map the so somehow it will map the point value into the index. And
Okay.
once for the model, it will
I see.
For the index. So because the index only have 2 bits, right?
But this can only save the memory of saving the model. When training, you still need to dequantize the model for training, which is still the model still have the same memory usage.
Actually, there are some technical somehow like the int operation, like the only use the somehow, for example, you only use the int 8 as do the multiplication and additive operation. So it means that it's possible to do the operators with the index, with the int thing.
That's weird. I think you have a dictionary, right? You have a dictionary map the code, namely the indices to the values, right? Like -0.75, 0.250, 0.75. Right? And when you do the inference, you should first decode the index and then ask them to compute and then propagate.
Yeah. So I missed that part. So if we don't consider, if we just consider the simulation of the quantization computation, so what it do is that firstly it gets the index and during the computation, it will convert back into those value, back into the float value, and then do the computation. So for this technique, what it saves is that so somehow for this the model size became much smaller, and when, as we know that in the computation in GPU, firstly it will fetch the data from the GPU memory, and then to some computation unit, somehow like the cache for the CPU. So in this process, the smaller the model, the faster the computation. So that's how it can speed up the computation, and also save the model size. I mean, it use the cost of computation to save the memory. That's the trade-off. This is
So
one thing. Yeah.
So when I do inference, so for example, I first dequantize this transformer block, and I do the computation, and I move to the next transformer block. The current transformer block is vanished, and I load another the parameters of another transformer block, and I use the dictionary to unpack the parameters. So that's how the quantization models do the inference.
Yeah. Sorry. I think
because the number. My question is because the number of the parameters doesn't change. So you still have the same number of parameters. You just find a way to compress it. So how do you use the how can you encode the flow number with the INT8? Or you use a dictionary?
It must store a table. So you can imagine that you have a table. So this is 0, 0, 0, 1, and this is still like 16-bit floating numbers.
Okay.
Just tell you, okay, if it's 0, 0, then you got minus 0.5, minus 0.25, 0.25, 0.75. And every time, because now her model are only represented by 2 bits, right? The whole model can be loaded into the memory, but you still need additional memory to store this dictionary. So when they do the inference, every time they first decode the weight according to those indices, and then they compute, doing the attention mechanism. You just compute the dot product and activation. You get the output for the next layer. Then they move to the next layer and then decode and do the computation.
Okay.
It's like you're decoding and you compute, and decoding, you compute, decoding, you compute.
Okay.
Yeah. So, that's one way to do that. So the benefit for this way is that, so firstly, when it fetch the data from the GPU memory to the computing unit, so it will become much faster, because currently the pipeline to fetch data to the computing unit is somehow the bottleneck, because the data fetching is pretty is a lot of workload, and yeah, and also there are some other edge device which can only support some computation, like the int8 computation. So that would be somehow different from what we just mentioned now. It will convert back to float and then do the computation. So for those edge device, it will do the operation on int8 directly. But we need to notice that actually we save the min and max value, so we also need the min max value to recover, or we can say the decode the index.
Hi Xin, it's Sui. So what's difference between we just run it up and mapping from the table? What's difference between them? I mean, if you have a number like 0.75, can we just run it up as a 75?
Yes.
I mean, what's difference between the table and just run it up by regular method?
If you just round up, is the memory usage is still the same?
What did you mean the regular rounding method?
Like the ceiling or the floor.
Oh yeah, it's the same. So yeah, it's the same rounding thing. Yeah. So because when we try to get the index, we need to do the rounding. No.
Then how much size the table is?
Let me explain this. I asked this question to you, Xin, before. You said doing this is the performance is very bad because it's the most straightforward way.
Yeah.
Right. I can do the rounding. I don't need to do actual coding, right?
What kind of rounding do you mean? Do you mean just the round to somehow, for example, we have the
point to the integers?
No, like if you got float 16, right? Why
not
it just converted into float 8?
Okay.
Okay.
You're gonna throw out several bits, right? I asked you this question before, and you told me that this does not work.
Yeah, I believe so. So yeah, the reason. Yeah. I think I can explain that. So so for currently for the we needed to know how the floating data point store in the memory. So I remember, so somehow for the float 16, so there are two parts. One part store, so somehow like the 1.2 e-5. So one part it was store this this one, and another part store the scientific things. So I remember this is how it divide into this one, and if it change to the somehow float 8, it will also have the similar formulation. The problem is that this method is static. So it will not use any xmin or xmax. So for all the data, no matter how it range, it always have the same mapping. So I guess that's the main problem lead to the bad performance.
I didn't get your point. I don't think so. I mean, I guess empirically you could conclude that doing this is not performing good, right?
Yeah.
Why people come out this binning and coding idea, but why it does not perform well? I don't know, because when you according to floating format, right? There's a standard format. If you convert it to float 8, of course, for the effective digits, you reduce number of bits to represent effective digits, right? And that kind of truncation, would that be like sacrifice accuracy? I mean, across different numbers? I'm not sure.
So my point is that like this. So for example, for the 2B, if we want to just somehow, if there, I mean, there is no float 2 data type. Assume there is a float 2 data type, and then what it can represent. I mean, the data maybe just so it from the 0 to 3. So maybe it just can represent the data range from somehow like the -5 to somehow 5. I mean there is only 4 float number it can represent. So with this, the large numbers in the real data will have large error, right? Because this is a static. It doesn't consider the rescale of the original data. Does this make sense? I mean, this is
maybe
just an extreme example.
Yeah, maybe it's just because the parameters has a lot of redundancies. It's not that the performance is not that sensitive to the actual values of the parameters. So you can use the very limited set of parameters to, well, imagine that you have a transformer block, you have many parameters. You can just use very some of them to represent them all. So it does not change the performance too much. But if you switch from float 16 to float 8, then so on the surface, you just see that I just changed the numbers of the parameters it can represent, right? But it also can affect the computations, like the matrix multiplications, the dot production is not that precise. So the error will propagate through the block to block. So you get a very bad performance. That's my guess.
Okay. Yeah, it sounds pretty reasonable.
Actually, in the quantization, when it do the computation, it will convert back to float 16 instead of
That's
so
that's a Shibo's point.
yeah. I mean,
I guess there are 2 points. One point is that using the binning and coding approach, you can compress more. You can save more memory. And the second is because when you decode, you kind of recover the representation in the original space. When you compute the matrix multiplication, all the other floating operations, you maintain the same error level as before, right? If you do everything in the float 8 space, your error could be amplified during the computation and forward passing.
For the computation itself, it will go back to float 16. Only the store use the somehow like the int 8.
Okay. And one more question. So if there's some parameter value outside the range, like -12 or 11, they will be represented as negative 0.75 or 0.75.
Actually, for the x min and x max, they also need to stored in the memory.
Also, okay, so they're gonna just look at the real x min and x max across the total number, total set of parameters.
Well, do the scaling in the decoder.
Okay.
So I believe with this, the process of the data would be better than somehow let's say there is the float 8 value, float 8 type.
Yeah, and does current method always use a even space binning, or they have some automatic method to determine the
yes,
binning
sure.
approach?
Actually, that's what I will talk next. There are two things. So the first thing for the round 2 nearest one, as we can say that, so somehow the distribution of the data is not evenly. So one thing we can do is that we can even ignore the outliers, the very large or very small values, but the distribute, just ignore the outliers and then shrink the range of the valid data, and this can improve the precision of the remaining data. That's one thing. And another thing is the quantization. So for this example, actually the distribution of the data somehow like the normal distribution. So it can instead of the evenly spaced method, we can use the quantization. So somehow we need to split all the data into 4 parts. But for those 4 parts, actually, we assume the data follow the normal distribution, and we try to make every part have the same area. So it's somehow like that. Here there are 25% data, and here there are 25% data. I mean for the normal distribution.
So when they decode, what's the value they're gonna take? Still take it or take.
So that would be a different mapping. Here I give an example for the int4. For int4, actually there would be 16 float value. It ranges from -1 to 1. This mapping table is fixed. So what we need to do is that we need to rescale the range of the real data into minus 1 to 1, and then found the mapping. I mean, and for a single value, get its indexed. With its indexed, it can get the corresponding value from the table.
Yeah, my question is how do you set this value?
Actually, you can just get the values before before the quantization, right? So they are fixed. You can calculate them, use the quantile function somehow.
So you mean you only use the quantile? It sounds weird. Like, I mean, if you got weight, right? Your code, your index following this range, right? Following this range, then what's the value should you take? Namely, this minus 0.696 or minus 0.525. How do you choose this value? So in your previously evenly spaced binning, you pick up the middle, right? And here, how do you pick up? You still pick up middle? Because if you want the area to be the same, that won't be -2 to -1, -1 to 2. If you want your probability cumulative density to be the same, it won't be evenly spaced in x-axis, right?
Yeah. Yeah, this is a very good question, and I kind of forget the detail how to.
Okay, so one more question. So your previous slides, you said like sometimes they can just ignore the outliers, but but what if you have some outliers? Wait, how do you recover it? How do you decode it? You decode it as 10 minus 10?
Yeah, so it will just recover to the nearest value.
So yeah, so if there's a lot outlier, it will either be Qmin or Qmax.
Yes.
Okay. So okay, so move to the next slide, which you were currently talking about. So for this one, what's the benefit of you're doing like quantile based quantization?
Yeah. So here this is the error distribution. So as you can see that, so when the relative error would be large for the value close to the mean and Qmin and Qmax, and for the other part, actually the relative error are small. That's the benefit. And if use the and so with this actually because the values close to the Qmin and close to the Qmin and the Qmax actually their the number of those values are small, so the expectation error would be smaller than the round to nearest method.
Oh, okay, I get it. So if you use the same number of the digits or indices using quantile can make the error on average smaller.
Yes.
It will be smaller than you just do the evenly spaced binning.
Yes.
Or in other words, I can say to achieve the same error, I can even use a smaller number of bins if I do the quantile based quantization, right?
Use the smaller.
Perhaps to achieve the same accuracy, if you do the evenly spaced binning, you might need 4 bits, right? But use quantile based, I can just, 2 bits or 3 bits are enough.
Yeah. But actually, there is one disadvantage of the quantile quantization, as we can say that the actually the error for the outliers, for the extreme values would be large. But as we know, the weight with large magnitude are important in the neural network. So if their error are large, it's possible to make the output for input of multiplied data. The error of this part would be large.
Okay, so yeah, but if you use a quantile based approach, because the outliers are small, right? If you look at the total average error, that should be still very small, right? Because you have a very tiny number of the tiny ratio of the outliers. Although for each outliers, you might have a bigger error.
Yeah. So actually, in practice, I think the quantile quantization is most efficient method, as I know. Yeah.
Okay, so now that so I guess that because outlier are important for the error of outlier is important for the performance, right? So why not people are using some heavy tail or flat tail distribution to do the quantile based quantization? Like I can use student T, right? I can use student T if I can transform the weights to be positive. I can use Cauchy distribution. I have a lot of choices. Why people just using normal distribution is going to be have very thin tail. Or do you see some work like trying to use other heavy tail distribution to replace normal distribution?
Not yet. The problem is that for the well-trained model, its weight always follow the normal distribution.
No, that's wrong. That's their guess.
Right.
There won't be any guarantee saying that okay, they always follow the normal distribution. Yeah, this assumption is wrong. Definitely wrong.
That's the claim in the Kilora paper. So
yeah, I think they don't understand statistics. Yeah, you even cannot justify this using large numbers law or whatever, because those weights are not independent. When you say okay, the average of those weights on average should converge to a Gaussian distribution, yeah, that's fine. But you're talking about the individual weights, and those weights are not independent. You cannot see that. And also the truth is not that, right?
Yeah,
If that's the truth, why do you see so many outliers?
yeah. Then the problem is that, so I think the benefit of this thing is we can just have one lookup table for all the data block, right? And if we, I mean, assume for the tensor 1, tensor 2, they have different distribution, and then we need a different lookup table to store the mapping between the index and the quantized value. I guess maybe that's another reason. So it will.
How do they store the tables? I mean, do they look at the total set of the weights across all the transformer blocks, and then they do the quantile? I mean, there is only one table, right, mapping the codings to the
Yes.
to the values. But you can also do that blockwise, right?
Yeah. Actually, they do that in the blockwise way. Actually, there are some blockwise dynamic quantization, and I can introduce this method now. So what is
No, we have not finished. Yeah. Yeah, I want you to go through every detail, because I really want to jump into this, not just have very superficial understanding. So okay, so if you assume those weights are following normal distribution, do they do any estimate?
Yeah. So
I mean,
no,
do they estimate, say, using maximum likelihood estimation to estimate what is the mean, what is the variance?
No, they didn't. So they just scale the value into the range -1 and 1. They didn't.
Even you reskew it,
Mhm.
It might not be the standard normal distribution. Your variance could be different, right? Your mean could be different. The mean couldn't be 0. It could be 0.05 or something.
Nothing in that part.
And if you don't know the mean and the variance, how do you do the quantile? The quantile is based on mean and variance. Right? The position of the quantile points are determined by the mean and variance.
Oh, okay. I see your point.
You can't assume like, okay, I rescue them to be between -1 and 1, then my mean will be 0, and my variance will be 1. That's not possible, right? Unless you do the standard normalization, as we did numerous times, right? I calculate the empirical mean and variance, empirical standard deviation, and then subtract the mean and divide it by the empirical standard deviation. Then I can roughly see this, right?
Actually, what they do is pretty simple. They didn't consider the real standard deviation of the data. So I mean, in this example, as you can say that. So there are this is the distribution. They are the fixed. So from -1 to 1. I mean, in each range, the value are fixed. And then what they do is that they just for the -10 to 10, they just rescale to the -1 and 1 and say which value located in which range. That's it.
So by scaling, you mean that you just divide each weight by 10? Or
Yeah.
Plus some shift, right? They do some linear shifting and scaling to.
In this way, they even don't do the
So they just divide it by 10?
Yeah, just yeah, I think
what if some weights are not between -10 and 10? What will happen?
I mean this is dynamical, so it will use the x mean and x max.
Oh, okay.
And somehow map to -1 and 1. So
Okay, there must be some linear shifting.
yeah. There is
Then
shifting.
they're assuming on the -1 and 1 there's a normal distribution and you pick up
Yes.
the quantile points.
Yes. Yes, but actually the real data may probably doesn't follow that. Yeah, you are right. But they didn't.
Are you sure they are really doing this?
Yes.
That doesn't make any sense.
The 25% is determined by the normal distribution or determined by
Yes.
the
Normal distribution.
But the
The
standard
standard-
normal distribution.
Standard normal distribution.
Yeah.
Yeah.
You need to, if for any normal distribution, if you want to know the quantile, like 25 or 75 quantile, it is determined by the mean and the variance. It's not only it's not constant. It's determined by the mean and the variance. If you don't know the mean and variance, how do you determine the? I'm just surprised if they do not.
So they assume
estimate.
they assume that it is a standard normal with 0 and 1 normal distribution, and they just cut the 25%.
Yeah, based on what Xin said.
Yeah.
looks
So
why
I-
don't they just build a histogram? Like I actually look at 20%, the range, how many the range contains 20% of the parameters or data points.
Yeah, they can do that as well. I mean, you can just sort them, right? Sort them, look at where's the position of the 25.
Yeah,
quantile,
right.
And
Yeah,
50% and 75%, right? You pick up that as your location.
Yeah. So for it, actually, it assume the data follow normal distribution, and after the linear transformation, it can become the standard one, and so it doesn't consider the standard deviation of the original data.
Yeah, I think they can simply retrieve some statistics, right? Based on that to construct the quantile position is much more sensible. Or like what Shibo said, you're doing this in a non-parametric way. You just sort them and look at where is the 75 quantile, 25 quantile, right? This is also feasible.
Yes, I think it's possible somehow.
Somehow they didn't do that.
No, they didn't do that. They rescale with the min max. They didn't rescale with the standard deviation.
Okay, where do they publish? Where did they publish this work?
Cullora, I think it
This work,
published
it's not
NeurIPS this year.
I mean, this method, the very method you're just talking about now, the quantile.
Oh, quantile quantization is in the previous paper. Quantile. Yeah, in the 8-bit optimizer while blockwise quantization. Yeah, I think this is a paper. It proposed the quantile quantization, and for the Cullora itself, actually it do the double quantization with the quantile.
Yeah, I'm just curious, where does this paper publish? Where is this paper published?
It's also some ICLEA or some NeurIPS paper. I remember last year.
Yeah. Can you just send me the paper title? I need to double check. This is surprising, right? Surprisingly coarse work.
Oh, that's the 2021.
That's fine. Let us continue. Yeah, it's the ICR paper last year.
Okay, yeah.
Yeah, I need to double check this paper because I can't believe they're doing this in such a way. So yeah, what kind of paper be accepted by
Yeah, I mean, yeah, you can go to the. Actually, they also released the code, so
perhaps they empirically work well, right?
yeah,
Or it's published in ICLR.
Yeah, last year's SAR. I just saw it.
Yeah.
Yeah, go on. She.
okay. You can see the shared slides, right?
Yeah.
Okay. So another basic technique is the block-wide thing. So somehow, as we know, the tensor are always very large. So as we can say that when we consider
when did you hop to tensor? I think you need to go to the last slide. I saw there one page about tensors.
This one?
The previous slide. One previous. I mean, go up. There's one more one previous page.
Just this one. I mean, block-wise dynamic quantization.
Okay.
So my point is that when we try to do the quantization, we always rely on the Q min and Q max. So as we know that when the Q min and the Q max are large, actually the precision of the quantization would be less. So the problem is that can we keep the Q min and the Q max in a smaller range? One solution is that we can divide the tensors into many small particle.
What do you mean?
And one.
What's tensor? What's the definition of tensor here?
The weight.
Okay.
Yeah. So maybe take the 2D tensor or the 2D weight, for example. We can somehow divide the weight in this way, and then it can do the block-wise quantization. It called the block-wise dynamic quantization, because in general the Q min and the min and max value for one small block is always smaller than the min and max of the whole weight. And another way to do the block-wise is it can do the column-wise or can do the row-wise. In general, it's always the column-wise. Yeah, it's pretty just some very simple method. In this slide, it gives an example how to do the block-wise dynamic quantization.
Okay.
Yeah.
So if you do this blockwise, that means you have to store more tables, right?
Yeah, sure. So it will increase the additional memory cost.
Okay.
But in general, the block size are large, somehow like the 64 by 64. So there are maybe then if the dimension of the somehow like the 1496, if the dimension is the tensor and the block size is 64 by 64, then there would be 64 by 64 blocks. So that this will cause the 64 by 64 by 2 additional float 16 values.
Okay.
Yeah, I think that's it. That's the very basic technical in quantization, and the core problem for the quantization is that how to reduce the average error, quantization error, and the most challenging thing is the outlier, somehow like the outlier in the weight. And also, when we try to do the quantization, it's also possible to do the quantization on the input, not only on the weight itself. Yeah, and yeah, I mean that's
How do you do the how do you quantize the input? What's the input? Input is a token, right?
Yes.
And you quantize it. What does it mean? Like token.
Yeah. So assume there are 40 tokens, and the dimension of each token is somehow like the 128. So it will try to quantize this whole tensor in the same way as quantize the weight.
But token itself, each token should be a one-hot encoding, right? Because you're generating sequences, right? Each token could be one word, right? You have a large number of words candidate.
Yes. So the quantization can be done in the token wise or in the whole tensor wise. In general, the token wise can perform much better than the tensor wise.
So if you're doing token wise, that basically you shrink the range of the words you can pick up to generate, right? Because your vocabulary can be very, very large if you want to generate a paragraph of text, right? Each text is it might be each word you might have like 10,000 possible words.
Yes.
And now you quantize it. That means you kind of merge many words together.
Oh, that's what. No, I don't think that will happen. So, I mean, so I mean, so for example, for each token, that's a 128 length vector, right? So for that vector, I mean, for two different token after quantization, they will still be different.
Oh, so you mean you have an embedding to represent each word. Once you have generated, you are only storing the embedding, which is a real value vector. Just quantize that.
Yeah. Okay. So I think when I say token, I mean actually that's the intermediate output of each layer. It's not the embedding of the.
Okay. Yeah, I again like forgot details about transformer, how I do the sequence prediction. I need to review it with you again sometime.
Okay. Do you mean do you want me to?
No. Just go to the next slide.
Yeah. So I mean there are actually For the quantization, actually, there are many components that can be do. If we want to do the training, do the quantization during training, actually, it's also possible to do to quantize the optimizer states. So, but that's not what we are going to discuss today. So today, firstly, we will discuss the quantization of the weight, and then we will, if we have time, we will go to the quantization both the weight and the.
Yeah, I still have some question. Like you said, you can quantize the input, I mean the intermediate outputs of the transformer. But why do you do that? If you're doing inference, you shouldn't do that, right? Because you encode it, you have to decode it to compute with the next layer, right? One transformer block, you got your output, right? Your output might be 128 by something, right? And if you decode it, if you encode it, and when you compute the inference, when you do the inference, right, when you generate final prediction, you have to decode it again and then decode the weights in the next layer and do the calculation and forward. Why do you want to encode that? Why do you want to compress it?
It can speed up the inference.
How can you add additional decoding step?
So there are two scenarios. So as we know, so for the large language model, actually in general, its batch size are small. If somehow like during the inference, we only have the batch size is equal to 1, then quantize only the weight is very efficient. But when the batch size are large, so somehow we do like the 10 or even larger. So the store of the
okay. So I mean you want to generate like 10 paragraphs in parallel. If you want to do that, you can use quantization of the input.
Yes. So because for the computation of every intermediate layer, you need to hold the whole represent the. You need to hold the whole tokens, right? So it may also need the quantization to fit into one GPU. And another benefit at what I said is the speed. So because in the computation of the GPU unit, it need to fetch the data from the GPU memory into the computation unit. And if it's stored in the float 16, it's still slow to fetch the data. That can be a bottleneck in the inference. Yeah.
Okay. So that means GPU cache you can store more tokens or more sequence tokens.
Yes, and also the bandwidth due to the limited bandwidth, so it can also help to speed up.
Okay. Yeah, I got it.
So it means that quantize both the weight and the input will benefit the inference or the training with large batch size. If the batch size is only 1, so I think only quantize the weight would be sufficient.
Okay.
All right. So before we go to the QLoRa, and I would like to introduce the general way to optimize the quantization. So it tries to minimize the quantization error of each layer. So the quantization error is somehow defined like this. So assume we only do the quantization of the weight. So the output of each layer, we want to minimize the area of the output of each layer. Yeah, that's it.
Okay.
And now we will go to the first method, QLoRa. QLoRa, the efficient fine tuning of the context large language model. Before we go to the detail of the QLoRa, we need to somehow review, somehow go through what's the parameter efficient fine tuning and what's the for fine tuning. So for the LLM, they are pretty large. So for some, if we have some new task, we can use the transfer learning to fine tune on the new task. And if we want to fine tune all the parameter in the large model, that's the for fine tuning. The disadvantage of the for fine tuning is that next time when we have another new data set, we will need to fine tune the whole data set again. And the fine tune and another thing is that because the new data set is always small, fine tune the whole large model is not efficient. So there is another method called parameter efficient fine tuning. There are two ways for that. For the first way is that assume we have a large model, we only pick up a small portion of the parameter to fine tune. Another method is that we add some additional parameter to the original model. This is also always called the adapter. And for the QLoRa, the idea comes from the LoRa paper. The LoRa paper is introduced only this year and has already become the most commonly used parameter efficient fine tuning method. This is the figure show how LoRa works.
Cannot see the figure.
You cannot see the figure.
Yeah, it's still your slides. It's still at quantization data with less bits.
Okay. I may need to show. My Mac is somehow kind of get stuck.
It's frozen.
Yeah. So I mean,
But it's still working.
It's my computer, it's my Mac get frozen. So
We need to restart.
yeah. I will come back in 1 minute.
Okay. So Hodge, given the limited time today, I guess you don't need to present today. Yeah, let's find some time like on Friday. I want you to present in front of me and Sina.
All right, all right. So in the Zoom.
Yeah, in Zoom.
Okay, okay. Uh,
Yeah, let's just rest for 3 minutes when to wait for Shane to come back.
Hi, I'm back. Can you hear me?
yes, yes, but I think the 闪电者told us we have a rest. We have 3 minutes rest.
3 minutes.
Yeah, yeah.
Okay. Okay.
Okay. Yeah, let's continue. Xin, you can start.
Yeah. Okay. So you can see the share the slides now, right?
Yeah.
Yeah. So before the QLoRa, I would like to introduce LoRa first. LoRa is the low it means the low rank. So what it do is it tries to add one adapter with low rank for the fine tuning. That is, it has a SAD connection for every weight. In this
You mean by SAD connection?
SAD connection, yeah. So it's somehow
Yeah. You mean sad? Feeling sad?
sorry.
What's
The
I mean, what do you spell the sad?
I mean the SIDE.
Side. Okay. Okay. Side.
Side.
Okay. Okay. Okay.
Okay, sorry for that.
Go on. Yeah.
Yeah, so this somehow like the ResNet, the residue in the ResNet, there is a skip connection. So, but but for this additional parameter, actually they have the low rank Indian. So for the dimension of the tensor A and B here, actually the tensor for the somehow for the A is with the dimension D by R, and the dimension for tensor B is have the dimension R by D, and the R is always very small, somehow like R is equal to 2. So this is the LoRa architecture, and during the fine tuning, it only fine tune A and B, and phrase the pre-trained weight.
So you mean between every linear transform block,
Yes.
actual weight matrix, they add this side component?
Yes.
Okay.
Yeah, and for the initialization of initialization of A and B is that the initialize of A is follow the normal distribution, and it will initialize B at 0.
Yeah.
And the QLoRa actually is a very simple modification on LoRa. What it do is that it do the quantization on the weight, and keep the remaining things the same. So it will do the fine tuning on A and B, but based on the quantized weight.
So so for the LoRa, for the method LoRa, even if you can do this, you still need a lot of resources, right? Because you have to You have to
Yes.
store the pre-trained weights, right? It cannot be.
Yeah.
Yeah.
So it needs some yeah. I mean, in general, it will fine tune on a small data set.
Okay.
But the fine tuning. I mean, in general, the training is always much more expensive than inference. So what I know is that the memory cost for the training can be 5 times as the memory cost of inference. So it would be pretty hard to do the fine tuning on a single GPU.
But with the QLoRa, they might be feasible, right?
QLoRa.
Because you can store the quantized pre-trained weights.
Yes, and I think the problem is that how to calculate the gradient of A and B. The gradient of A and B somehow dependent on the input, right? Here the input is X, the output is H, and for the X, actually that would be involved in the gradient of A and B. So the storage, the memory cost for the gradient will not be small.
Yeah, of course, but at least you store the model. You can download you can store your whole model in one GPU right now, and when you do the training, when you're training, you have to store all the gradient. You have to pass the gradient from block to block. When you backpropagate the gradient with respect to B and A.
Actually, what I know is that so when we do the training of the model, all the gradient will be held in the memory together. And but I know there is some technique that can optimize the storage of the gradient. It can somehow. I mean, when the gradient is useless, it can just discard that part. This is called I suddenly forget the gradient checkpoint. Yeah, there is a technique called gradient checkpoint. That's a way to manage the gradient in the memory, like what you mentioned. And also there are some other technique to manage the memory somehow, like the page fault in CPU.
Okay. Page fault. Okay.
Yes. Yeah. So.
Yeah, my point is that with the QLoRa method, it is possible for us to fine tune a large language model, right? Because you can store a large language model with quantized version, and then add additional side components and to do fine tuning on small data set.
Yes, I think the of course the cost of the QLoRa would be much less than LoRa because the per trained weight would be only a quarter of the original model size, but the training itself, I think, is still cost.
Okay.
So another thing I would like to mention here is the quantization of the weight. Actually, so firstly it uses the normal float, the quantum quantization we introduced before, and another thing it uses the double quantization. the double
So
quantization.
B is initialized as zeros, not B is equal to
Yes.
zeros, right? Okay.
Yeah, it's the initialization. Yeah.
Okay. Yeah, makes sense.
All right. So for the double quantization is somehow like this. As we know, when we have a large weight, large tensor, it will do the blockwise quantization. It means that in each block it uses the normal float quantization. So for each normal float quantization, we need to store the mean and max pairs. And when the tensor size is pretty large, so from somehow have the 4096 by 4096, and we have the small block size like the 64 by 64. Then we still need to store a lot of min and max pair. What it do is that for the min and max pair, it will do the normal float. It will do the quantization again, and so it will have the min and max prime to store the new information, and then it can furtherly reduce the additional space cost to store the min and max. And yeah, so here I just passed some formulation in the paper here directly. So when during the computation, when we it will convert back to the float 16 and the double dequant. So for the C1 and the C2, that's the constant. Actually, that's the min and min max pair we used in the quantization. Yeah, as you can see here, for all the calculation, they use the float 16.
What does L1, L2 mean?
That's the A and B. Yeah, because I just use different annotation from
Okay,
different.
this is how they compute each layer.
Yes.
And then they do the back propagation.
Yeah.
Okay.
So L1 and L2 are trainable.
Okay.
And for the others, they are fixed.
And L1, L2 are always float 16. And you back propagate the gradient and just update them.
Yes.
Okay.
So there are some experiment result on the Llama model. Llama is the open source large language model. So for ChatGPT series models, they are not open source. Yeah, and for the 4-bit Llama, actually, the blue curve indicates the float 16 performance, and the yellow one indicates the quantization, and the green curve indicates the double quantize technique. So as we can say, actually the 4-bit double quantile quantization can achieve
better accuracy?
Yeah.
That's a little weird, right? Because you do double quantization, you kind of like introduce error of the max and mean. Well, how can it be better than you only do the single normal float quantile.
Yeah. Actually, the x-axis is the total model bits. So it means that because the quantization makes the model much smaller, and I think this evaluate. I mean, somehow like that the model 30 billion after quantization will become the model somehow like the 4 billion. So it will compare the quantized model with the original somehow like the 4 billion model. It will
Also,
not
the x-axis
compare with the original model.
x-axis shows the size of the quantile model. With the size of
Yes.
the quantile model.
Yes, the model bits, not the number of the model parameter. So it means that with the same memory cost, quantization can achieve better performance than the original model.
So performance here means what? Means accuracy. I mean accuracy. What does it mean?
Yeah.
What does accuracy mean here?
So for there are some text. I mean, for the text generation, it can viewed as some classification method, right?
Also,
problem.
so it measures accuracy in generating.
Generating the better the higher the better. So when the model, the cost of the memory for the model is the same, the QLoRa can perform better than the original model. Yeah, that's it.
And what does 4-bit llama mean? What does it mean for 4-bit here?
It means that it will quantize the model weight into 4-bit.
Okay, if you quantize them with 4-bit, then how can you vary the total model bits? Because all the weights are quantized by 4 bits, right?
Sorry, I didn't get your question.
I mean, if you have decided to quantize every weight into 4 bits, then your model bits should be the same, right? Should be fixed. How can we vary the total model bits?
Yeah. So assume we let's say we have a 16 billion model, and then for this actually the bit for this is the 16 by 16 billion by 16, right? Because for every weight it uses the 16 bits. So this is the total model bits.
So this is the size of the original model?
Yeah. And when it quantizes into 4 bit, so it will become 16 billion multiply 4 bits. So the model bits will reduce to a quarter of the original one.
Yeah, but what does total model bits mean? Is the first one or the second one?
This is the original model. The memory cost of the original model. This is the quantized model, and for the quantized model, it will compare with a model of 4 billion parameter. So it will outperform this one, the 4 billion model, not outperform the original 16 billion model.
Yeah, I mean, what does the x-axis, which does the total model bits, the x-axis correspond to? It correspond to the original model size or correspond to the quantized model size?
I mean, for the blue curve, actually, that's the accuracy of the original model, right? I mean, actually, there is a serious model. There can be somehow like the 7 billion model, 13 billion model, and 33 billion and 65 billion model.
Okay.
So it
So
will
it says-
contain each model into four bits.
Oh, okay, I got this point. Okay, so
Yeah.
red line, the blue line just means if you don't do any quantization, you maintain the original model size. If you
Yes.
vary the model size, how does the accuracy vary, right?
Yes.
And the yellow line and green line shows that after quantization, if you occupy this much model size, how will that perform? Actually, there's different size of models.
Yes. I believe so. For those three models, they have different number of the parameters.
In the original model.
Yeah.
Oh, okay. Then that makes sense. That basically means okay for the yellow, for the green one, because you take the same model size, but you're compressing a larger model.
Yes.
And that larger model performs better. So that's why its compressed version also performs better.
Yes. So with this, we can show that the QLoRa can make the memory become more efficient with regarding to the accuracy.
Okay.
And in this table, it has show the performance of the QLoRa with different quantization. So for the
and FP forming.
This is the float point 4. Float point 4 is some you can regard this as the what we just mentioned round to nearest.
Oh, really? Okay.
Wait. Yeah. This is just use the round to nearest. Yeah, I believe. And the NF4 is a normal float.
And what does int8 mean?
So firstly, actually, the so firstly, this is quantized into 8 bits, but I'm not sure when do the computation it uses the int8 because currently the CUDA and the CUDA can support the int8 computation. So I'm not sure whether it uses the int8 computation or use the float operator. I guess it can use the int8 directly, but I need to check how it incorporate the min and max value, the float values during this operation. Actually, for QLoRa, the underlying code base is bits and bytes. They are implemented in the C++ and CUDA. so they can do some optimization based on the hardware.
But for
I-
int8, I'm just unclear about that. Like, you do the quantile, right? You do the quantization. You do the quantization, you convert it into 8 bits index. But when you decode, you still need to convert it into a float, right? What's the difference between int8 and NI4? The decoding procedure is the same or not?
For this, actually, I need to check the code. So, firstly, I'm sure for the int8, it still need to access the min and max stored in the memory. But I feel it somehow convert this floating point into the int type.
Here?
Yeah, and then do the multiplication and additive operation in the int8 thing, because this can make it faster. That's what I understanding, but I'm not sure. I mean, if it uses the float thing to do the computation, it just somehow say FP8, not the int8.
Yeah, I understand, but okay. Then you have to multiply them by some number, like to make it to be as large as possible, right? So that you can treat.
Yeah,
You
there
take out the integer part.
can be overflowed.
Okay.
Yeah, for this I have verified. But for the because why it supports the int8 is because some edge device only support the int8 operation. It cannot do the float operation.
But you have to use some mechanism that you first scale the floating stuff, right, into an integer.
Yeah.
Operation is still
yeah, this is implemented by the bits and bytes. Bits and bytes is the Git repo released by the University of Washington. And for this paper, like the Cullora and some other paper, like there is one paper just called int8. So for actually they come from the same lab. They provide some very some code close to the hardware. They can support such operation. So when if I want to calculate, I want to do the computation in int8, we don't need to worry about how the hardware will do and how the API will do. So we can just call some API for that directly.
Okay.
Yeah.
Okay. What else do you want to say about the Cullora?
I think for Cullora, that's it. And
Okay. Yeah, I guess Cullora, the major contribution is just the double quantization, right? Because the functioning architecture is the same as LoRa.
Actually in technical the technique in Cullora is very minor, but it's a significant paper to quantization. People say that Cullora is like the ResNet towards the traditional convolution network. Yeah, it just makes the quantization perform much better than the previous method.
Because of this nested structure, it introduces, right, the double
yes.
quantization, because
Yes,
you have an effective way to encode the meta information. Meta information here, I mean the min and max values.
Yes.
Okay.
So yeah, actually, as we can see that the parameter efficient fine tuning works well, but it still doesn't works well as good as the full parameter for fine tuning.
Full fine
And
tuning. Okay.
for fine tuning, yeah. And on another side, it requires additional parameter. So that's why I want to do the tensor decomposition for the original model. With that, I actually it's possible to, I mean, it at
From the full
first
model?
yeah, firstly it's a parameter. There is no additional parameter required, right?
No adapter. Also, you mean, okay, I kind of forget what's your motivation. So your motivation is also you want to provide a way to fine tune the full model, not just adding an adapter.
I think in the first step we will not do the fine tuning. In the next step, I mean, if our first idea work, my plan is that we can fine tune one tensor decomposition component and keep
So
the
you just want to fine tune one part of the parameters, not like introduce
yes,
additional component.
yes, and for this it will not introduce additional data, and also it's somehow possible to decompose. Decompose the model into different component and make each component response for different tasks. So this will make the large model become more flexible and pluggable.
Okay.
Yeah, but that's the future work. I mean, if we I hope we can make the first idea work, and along that we can do more paper on that. Yeah.
Okay. Yeah, very good. Yeah, I mean, due to time limit, let's stop here today. Maybe next week, Xin, you can continue the introduction of the quantization works for LLMs. Okay. So any questions so far to Xin? Okay. Yeah, let's stop here today.
Okay. Yeah. Thank you, everyone.
Thank you.